this is problem 5. For this problem, again, we need to use the graphical method to determine the shear and moment diagrams for this beam. So the first thing we want to do is to determine all the support reactions. So this is from point A to point B. We have distributed load this much is 0.5 times 6. So that is going to be 3. So 3 right here in the center, 3 kip. And then this much is 0.5 times 6 divided by 2, so 1.5 right here. And then we have a 5 kip force right here. And then this distance is 3 feet. This distance is going to be 8 feet. And then we can solve for the support reactions at point A and point B. So again, that is a rigid body equilibrium problem. Shouldn't be difficult at this point. So at point A, we have 4.875 kip. And at point B, we have 4.625 kip. So now we're actually ready to draw our shear force and bending moment diagram. So starting from point A, that is 4.875 up. So we start from here. .875 in the unit of kip, kilopound. And then we have a constant slope of negative 0.5. Therefore, Vx decreases, but decrease by how much? It decreases by this magnitude of 3, which is 0.5 times 6. So 4.875 minus 3 equals to 1.875 here. And then it continues to decrease, but not as a straight line anymore because the slope changes. The slope, however, changes from a high slope to 0. Therefore, the decrease will get flatter and flatter. So initially, the decrease is rapid, and then it's going to get slower and slower until it reaches a slope of 0. So that's the shape for the second half. But by how much? It's going to decrease by this much, 1.5. That's the magnitude here. So 1.875 minus 1.5, it's going to decrease to a point that is here with a magnitude of 0.375. For the next region, nothing changes. W is 0, the load intensity is 0, no change in shear force, so it's actually a straight line, getting difficult to draw, but very close to the x-axis, a straight line here. No change. So at this point, it's still 0.375. And then we have a concentrated force. Therefore, that corresponds to a step change in the shear force diagram of 5. So we start from 0.375, decrease by 5. So it reaches negative 4.625. And then for the next region, nothing happens, no change until it reaches this point right here, still negative 4.625. But this concentrated force at point B returns the slope back to 0. So that's the shear force diagram. For the bending moment diagram, because this beam has no couple moment, external couple moment at point A or at point B or anywhere else, therefore the graph of bending moment starts from 0, ends at 0, and there's no step change because there's no external couple moment. So for the first region, the shear force changes from positive 4.875 to 1.875, still positive. Therefore, the bending moment keeps increasing, but it has a rapid increase in the beginning because the slope is larger, and then the increase gets slowed down. Therefore, from here to here, it's like this. This is still not plateaued yet because this is 1.875, not 0. And then it keeps increasing, but again, the slope is getting smaller and smaller, still positive. Therefore, it still increase, but the slope is getting smaller and smaller. And then at this point, you have a constant 0.375 kip in the shear force. Because it's a constant, therefore there's a constant linear change. Very difficult to draw right here. You just need to know that it is a constant linear change, increase to this point. And then for the next region, we have negative shear. Therefore, it's a decrease, constant decrease. You draw a straight line. Remember, the bending moment has to return back to 0. So from here to here, all the way, the bending moment keeps increasing, even though the rate gets smaller and smaller. And then for the last region, it just has this linear decrease back to 0. Therefore, as you can tell, this is where we have maximum bending moment. And how much is that? Well, remember, this is 0, this distance is 6, and this slope right here is a constant 4.625 negative because it's decreasing. Therefore, this point right here simply equals to 4.625 multiplied by 6, and that is 27.75 kip foot. So that is the maximum bending moment, and most of the time we are actually only interested in where the maximum shear force or bending moment occurs, because that's where the member is most vulnerable, is most likely to fail.